Okay, greetings math people, and welcome to lesson 2 of differential equations. So in lesson 1, we looked at a differential equation that was primarily a function of x. We looked at an initial value problem where the differential equation was primarily a function of x, and we went through and solved, and we developed a little formula as well. Today we're going to be looking at more application, a couple of application problems based on what we already learned in lesson 1 and some things we can take from calculus. So let's go ahead and get right into it.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relaxed one.
All right, so again, in this particular lesson, we're really just going to be doing a couple of application problems, just 2, I believe, and we're just getting in the habit of applying what we learn, being able to use what we learn and get the information that we know and be able to solve, application problems. So that's kind of the gist of what we're doing today. And just want to remind you of a few things we learned in calculus that will come in today, and that is the position, velocity, acceleration relationship. And so just to review quickly, you have a position function, and then let's say the position function, which would give a position of an object at a particular time t, is a function of time, and let's say it's measured in meters. And if I take the derivative of that position function, when you take a derivative of a function, the units of the derivative are the units of the original function per the units of the independent variable. So if the position function is a function of time and is measured in, say, meters, then when I take its derivative, that derivative is going to be measured in meters per second, the units of the original function per the independent variable. And that, of course, represents velocity. And so the derivative of position is velocity. And then if I take the derivative of velocity, which is a function of time, which is measured in meters per second, then its derivative is going to be meters per second, or meters per second squared, which of course is acceleration. So the derivative of position is velocity. The derivative of velocity is acceleration. And since velocity and acceleration are derivatives of other functions, we can consider those differential equations. So we're going to use that understanding that velocity and acceleration are differential equations, and we're going to use that to solve a couple of application problems. So let's take a look at the first problem we're going to solve. So I'm going to read the problem. And the problem states, at an accident scene, the police investigator is attempting to determine the rubber marks on the road, from the rubber marks on the road how fast the driver was going. Suppose it is known that this particular car brakes with a deceleration of 15 meters per second. At what velocity was the car going at the moment it applied its brakes if the car traveled 75 meters before it stopped? All right, so we want to write down the necessary information in this particular problem. So one thing is that stated is that it brakes at a deceleration of 15 meters per second. So that means the acceleration, which I'll call A of t, is negative 15. Since it deaccelerates, the acceleration is going to be negative. Also, it states at what velocity was the car going at the moment when it applied its brakes if the car traveled 75 meters before it stopped. So the car travels 75 meters before it stopped. So I'm going to let TF be the final time, or the time that the car stopped. And therefore, X of T sub F is going to be 75. All right, and then let me just state what they want me to find. So I'm just going to briefly read the problem again. At an accident scene, the police investigator is attempting to determine from the rubber marks on the road how fast the driver was going. Suppose it is known that this particular car brakes with a deceleration of 15 meters per second. At what velocity was the car going at the moment it applied its brakes if the car traveled 75 meters before it stopped. So it wants to know the velocity the car was going when it applied its brakes. And so I'm going to call that the initial velocity. So we're going to find a v sub naught. So I'm going to consider the time the velocity was going when you hit the brakes as the initial velocity. So we have an acceleration, we have a position function relationship, and they want us to find the initial velocity. So again, let's work our way back. And so we have the acceleration. So from the acceleration, I can find the velocity function. And so if the acceleration function is negative 15, then the velocity function would be negative 15t plus some constant, and that constant happens to be the initial velocity. So notice, and this is the guy I want to solve for. So I want to solve for the initial velocity. Now, I have this guy t sub f, which is the final time. And I know a couple of things about t sub f. I know the position function at t sub f is 75. But there's another thing I also know at t sub f. And so t sub f is the final time. That's when the car stops. So when a car stops, the velocity is 0. So I also know the velocity at t sub f. So if I evaluate this function at t sub f, v of t sub f is going to be 0. And I'm just plugging in t sub f for t. And so this will be negative 15 times t sub f plus v naught. And that means that v naught is 15 times t sub f. And that's relationship with v naught in terms of t sub f, but probably what would be more beneficial is t sub f in terms of v naught. So t sub f is v naught over 15. Okay, so that's going to prove to be an important figure there. All right, so again, I'm trying to solve for the initial velocity. So what I want to do is solve for the initial velocity. Now I know that the initial velocity is 15 times t sub f, but I have no idea what t sub f is at this moment. But I do know that the position at t sub f is 75. So let's find a position function. So again, we're going to integrate the velocity function to get the position function. And so the position function, which I'll call x of t, you can call it y of t, x of t, s of t, or anything of t. But for this, I'll call it x of t. And that'll be negative 15 over 2 t squared plus v naught t plus the initial position. To make this easier, I'm just going to say that the initial position is 0. So plus 0. So what I'll do is I'll plug in t sub f into this position function. And I know x of t sub f is going to be 75. But I'm going to plug t sub f in terms of v naught because I can solve for v naught. So if you think about it, this will become 75. This will become something in terms of v naught. This will become something in terms for v naught. So it's going to allow me to solve for v naught, which is what the problem wants me to find in all. So running out a little bit of room. So let me rewrite this statement on a blank sheet. And the statement is that x of t is negative 15 over 2 t squared plus v naught t. And I'm going to plug in t sub f for t, and x of t sub f is 75. And remember, t sub f in terms of v naught is v naught over 15. So I'm going to be plugging in v naught over 15 here. So this is negative 15 over 2 times v naught over 15 squared plus v naught squared over 15. So again, remember, t was v naught over 15. So v naught over 15 times v naught is v naught squared over 15. All right, so let's it's just arithmetic from here. Maybe a little bit of algebra, I guess you could say. So here I have 15 squared, of course, is 225, but there's really no need to square it because I have 15 times 15, and we'll take one of those 15. So that'll just leave me with a 15. And this V naught will be squared. So there was 15 squared, 115, cancel that. So this is going to give me negative V naught squared over 30, 2 times 15, negative V naught squared over 30. Plus, I'm just going to make common denominators. I have V naught squared over 15. I'll multiply by 2 over 2. So plus 2 V naught squared over 30. And if I add those two guys together, I'll just get V naught squared over 30. So V naught squared over 30 equals 75. And now all I have to do is multiply by 30. That's 2,250, and take the square root. So V naught is the square root of 2250. All right, I hope that made sense. That was our first application problem. I thought it was pretty good. And again, we're just applying things we learned previously in calculus about position, velocity, and acceleration, and about, how to solve differential equations as we learned in lesson 1. All right, we'll look at one last application problem. And so let me read the problem. An overly cautious traveling distance between you and a car in front of you would be the distance it would take to stop. At a speed of 60 kilometers per hour, how far does a car travel if it decelerates at 2,500 kilometers per hour squared? So at a speed of 60 kilometers per hour, so we're going to say our velocity, and I'm going to call this the initial velocity, is 60. And so how far does a car travel if it decelerates at 2,500 kilometers per hour squared? So the acceleration is 2,500. And how far does a car travel? So it wants me to find how far the car traveled from this time, how far the car traveled as it deaccelerates until it stops. All right, so again, so I'm going to refer to TF as the time it takes the car to stop. And I want to see how far the car travels. So I want to find X of T sub F. So again, T sub F is the same thing as the time it takes for the car to stop. So this time it's not given, so it's a little bit different. All right, so again, let's just begin the process, and let's start off with the acceleration, and work our way to velocity, and if need be, work our way to position. All right, so the acceleration is, and I could have wrote this as a function of t. A of t is negative, and I didn't write negative, apologies. It's negative 2,500, and it's negative because it's decelerating. So that means the velocity function will be negative 2,500 t plus the initial velocity. But I know the initial velocity. The initial velocity is 60. All right, so that was pretty beneficial. Now, I would like to find the value of t sub f. Now again, when the object stops, the velocity is 0. So if I plug in t sub f into this velocity function, this is going to equal 0. So 0 equals negative 2,500 times t sub f plus 60. And so I can solve right for t sub f here. So t sub f is going to be 60 over 2,500. 60 over 2,500. Let's see. Let me get rid of a 0. And let me divide by 2. So this is 3 over 125. So I know t sub f. Again, I'm trying to find x of t sub f. So I can, integrate the velocity function to find x of t, and just plug in this value for t. So let's get the position function. So the position function, which I'll call x of t again, it'll be negative 2,500 over 2, so negative 1250 t squared plus 60t, plus the initial position. Again, I'm going to make the initial position be 0. So now, to solve the question, all we have to do is plug in 3 over 25 for t, because 3 over 25 is t sub f, and I'm trying to find x of t sub f. So x of 3 over 125. And now we're just doing a little arithmetic. So this should provide our answer. So we have negative 1250 times 3 over 125 squared plus 60 times 3 over 125. All right, so let's do our little arithmetic here. So again, there's no need to square this. I mean, I could square it. It would be 15625, but there's no need to square it. So I have, 125 squared. Well, that 121 of those 125s, I shouldn't have crossed it out. One of those 125s will go into this guy and make that negative 10. So I'm still left with a 125 here. And 3 squared is 9. And so that's going to be negative 90 over 125. If I can, just let me fit it in right here. Negative 90 over 125. And look what we have over here. We have 180, positive 180 over 125 plus 180 over 125. And so what we get is 90 over 125. And we can reduce by 5. We can get 18 over 25, or 0.72 if you want the decimal. But this indeed is our answer. All right, so that's going to conclude our lesson 2 on differential equations. On our next differential equations lesson, we're going to look at separable, first order separable differential equations. We will see you next time.
First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing. Problem after problem until the day's end. Solving, keep solving, and turn the page in, and still keep grinding. Solutions keep finding. I have never seen a problem